Once again, welcome back. This is now the third video in the Eisenman Memorial. We've completed steps 0 and step 1. As a refresher, step 0 had to do with creating the rectangular grid, going ahead and importing a site boundary curve, and culling or removing any points that resided outside of that site boundary curve. Step 2 then was all about projecting those culled grid points down onto the undulating surface. You'll see it better here in perspective, like so. Measuring then the distance from those newly projected points that are on the undulating surface to each of the imported attractor objects and finding out what was the minimum distance for each of these, which grid point or which attractor object was the closest to every single one of these grid points, which is our minimum there. The next step that we're going to do, and I'm going to turn some of this other older information off. Okay, we'll just leave on the projected grid points like so. The last step for now is to sort these distances, adjust the height to match the maximum height of our stellas, maximum allowable, so that the ones around the perimeter are essentially 0, and the one that is furthest from any attractor object, so if I look in here, things that are going to be far away from the site boundary curve and the attractor objects, maybe over here, will also be very minimal. Or excuse me, the ones that are furthest away will be the tallest. The ones that are closest to the attractor objects will be the smallest. We will come back later, and we've only added these two attractor points and attractor curve in here, but we'll come back later and add the boundary curve also as an attractor object to push down the perimeter ones. That's simple enough. We can just add that as another attractor object up above here. But for now, we're going to go ahead and focus on these operations. Sort the distances, adjust the heights to the maximum height of the stellas, and create a box using XYZ distances and these surface center points. So we need all this information. We need to bring down the dimensions of the boxes, including the XY and the maximum Z height. We need the box surface center points to be able to do that. I've given you all that information at the very beginning. We said go ahead and make these panels that have the X, the Y, and the maximum Z height. We're going to go ahead and bring those down. Now, instead of bringing them directly down like with these actual panels, I want to leave these panels up here so I know that they're available and bring these just down with number components. So we're going to go to parameters, primitive, and we can use either integers because they are integers and likely will remain integers, or more accurate would be actual numbers in case they ever have decimal places within them. So let's go ahead and drop in a number component. Again, we're going to go ahead and wire these together. So we're going to wire it like so. I always relabel this component to match the source that it's coming from. So I'll relabel this as X dimension. And I'm going to go ahead and set the wire display to be hidden. I'm going to go ahead and do that 2 more times for each of my other operations here. There we are. So now we have 3 wireless receivers that match our dimensions. Let's go ahead and bring those down to the third step here. The other thing that we are going to need is our surface CPs. These are all the points that are projected onto the undulating surface. We'll find that back up on this second step, step 001, and the coming out of our surface CP are all these points. We want those. So let's go ahead and use a point container. Go to parameters, geometry, and point. And I'm going to call these surface CPs. Surface closest points, wire display, hidden. There we go, and we'll bring this down below. There we are. Okay, I'm actually going to organize these slightly different because I know I'm going to want my points to be above it, like so. Okay, so now to do this, what we want to do is create an actual geometry, an actual block that resides at this center point. So to do that, we're going to go to surface, we're going to go primitive, and I want you to use the center box component. This is going to create a box based off of a center point, and it has X, Y, and Z values. So I'm going to go ahead and drop that in. The B is the base plane. By default, it's set for the world XY. This is essentially the centroid of the object as well as the plane that it is square to. Now, I know I've always told you that you have to give apples to apples, oranges to oranges. So if this is asking for a plane, you have to give it a plane. But there are several exceptions to that rule. If you feed an object a plane input with a set of points, it's going to assume the XY as the grid, and each of those points is the new origin of that plane. So what I'm going to do is I'm going to actually feed, even though these are points, and this component is actually asking for planes, I'm going to feed those points in, and it's going to make little XY planes at each of those locations. And because of the fact that these already have values stored in the X, the Y, and the Z, all just a value of 1, if you look very, very closely, and I'll see if I can even zoom in close enough, like so, you see you get a little box that's centered around each of those points and is square to the XY plane, because again it assumes the XY plane. Now what we can start to do is feed in our X and Y dimensions. We don't know our height quite yet, we'll deal with that in a moment, but we do know that our X and our Y are already set. So let's go ahead and feed the X into the X and the Y into the Y. And we're going to have our first issue right away. And you'll notice your first issue is that they overlap, and they're not supposed to overlap. We should have them spaced far enough apart that they don't overlap. Why are they overlapping? And here's exactly why they're overlapping. If you'll notice, the box is based off of a center point. The dimension in the X that you are feeding it, it is actually making that dimension in the positive and the negative dimension. Essentially, it's making a box that's twice as wide as what we want. The same is true in the Y dimension. It's making it twice as long in the Y axis as what we want. So when we have an actual finished dimension coming from this X dimension component, we need to go ahead and divide that in half before it is used as our box, because that way we will offset properly in both directions and the boxes will be the right size. Remember, you can do something simple by going to math, operators, and using a division and dividing this by a value of 2. We can also do this in a couple different ways by embedding the expression. And this is another scenario where I like to embed the expression so I don't have as many components kind of clogging up my space. To do that, I'm going to right click on the X input. I'm going to go to expression here in the middle. I'm going to type in the expression of X divided by 2. Okay, don't put a space, enter anything, just use the X divided by 2 and commit to changes. You'll get an asterisk, and now you'll see that they no longer overlap in the X dimension. We're going to do the same in the Y. So I'm going to right click, expression, right click, expression. We're going to say X is always the variable. So even though this is a Y input, we're going to use the formula of X divided by 2 because X just represents the variable even though it's labeled as Y in this scenario. So X divided by 2 there, hit commit, and there you go. Now our stellas or our boxes actually are about the right size. Now what we need to do, I'm going to go ahead and drag this kind of over to the end here because we need to do a few things. We need to go ahead and use the distances to create the heights, the Z heights. And we have all of our distances from the last step. After all of these minimum, we finally find what is the distance to the closest attractor object that's coming out of this minimum. Those distances are numbers. So let's go underneath parameters, primitive, and number component. We'll wire that in. We'll call these our distances, or I'll call them my min distances. We're going to make this a wireless receiver, so we're going to go ahead and right-click Wire Display Hidden and bring this down below. So those are our actual distances. This is our maximum allowable height. This is where we're going to go ahead and use that whole remap idea, because if you look at these maximum distance or these minimum distances, they're outrageous. They're quite large. Here, this one's 2,000. We can't have stellas that are 2,000. We know that the maximum stella allowable is 189 inches, okay? So we can't use these distances as is. We have to scale them down or proportionally reduce them so that the tallest one becomes 189 and the shortest one becomes 0, basically. Again, we're going to do that with the remap component. To do that, go to Math, go to Domain, and Remap Numbers. 3 inputs. The values as they are, the source domain, which is essentially the largest and the smallest value coming from our minimum distance, and the target, the largest and smallest allowable or desired Our largest desired is this maximum height, which is 189. The smallest is 0. So we can easily make a domain like so. So let's start by wiring in our minimum distances as the actual values we want to rescale or resize, reproportion. Let's skip this source for a moment and let's work on the target. And the target is easy enough. It's going to be 0 to 189. 0 is the lower limit, 189 is the upper limit. If you remember right, last time we did this, we went to domain, math, domain, construct a domain. We put a lower limit into A, and we would use this into B. But I also told you if you don't use this domain and you wire in a number straight into something that's asking for a domain, it assumes 0 is the lower limit. So now if you hover over that, it assumes 0 was the smallest one, which was accurate, which in this scenario is right, and 189, or the value we wired in, becomes the upper limit of that domain. So that's perfect. That domain will work just like so. We really only need to generate the source domain. To do that, we're going to use this whole minimum. We're going to create a new source domain using this domain here. We have to cherry pick the largest and the smallest values in here. Now again, all of these values are in those individual lists. Here's a row of points. Here's another row. This is that kind of idea of the dresser with the objects inside of those, okay? We can't just sort these, right? I can't just simply right click on here and sort them or run them through a sort component, because if I go to sets, list, and sort list, if I sort them, it will only sort them within those lists. So it sorts the first list and the second list and so on and so on. What I want to do is get them all into one giant list and then sort them. So I'm going to go ahead and right click to flatten. So I can right click on the K input and flatten. That puts them all into one massive list and sorts them as one massive collection. Now we see the smallest one is up top, that's 16.32 in my scenario, and the largest one is at the very bottom. To pull out the smallest one, we can use this index number that resides on the left. That's the 0 index number. So let's go to sets, list, list item. I need a little more room in here. Just give myself, stretch some of this stuff down. There we go. List item. The list of data I want to sort through to pick out is all of these sorted lists. So it's the K coming out of here that goes into the list of data. The I is the index number that I want. I want the 0 index number. By default, 0 is already stored in there, so we don't even have to put anything in there. And W is the wrap. We don't have to worry about that. All we want is one value. That's the very top value at the 0 index, and which is what we get as a result. We just get that one value. Perfect. That's going to become our A, our lower limit of our domain, our A input of our domain. Now we want to do a very similar operation, but this time we want to pull out the very last item. We can't just list this last index, because if our grid ever shrinks or expands, that index number will change to add more or remove points. So what we want to do is we want to flip the list around so that it goes from not from smallest to largest, but from largest to smallest. So what I'm going to do is I'm going to do another list item, go to sets, list item, and I'm going to right click on the L input and reverse that list before it goes ahead and lists the item. So by reversing the list before it went in here, you could also, by the way, go to sets, list, and reverse a list, and that component just looks like so. And within the component, it will reverse it, but we've actually embedded it within the input of this list item component. So now we've reversed the list, still cherry picking the 0 index, and now we should have the largest value of all of our distances. Perfect. That largest value is going to become the B of our domain. And now our new domain says something very small, 16.32, to something very large, 22.15. That domain is going to become our source domain, and these remapped numbers all become our Z heights. Now, if you haven't saved lately, you should probably save before you wire this together, because what's going to happen is it's going to do a lot more calculations. But there you go. Now you'll see the stellas that reside closest to the attractor curve and attractor points are the lowest, and the ones further away are the tallest. Let's go ahead and just quickly organize this. So I'm just going to select all these objects, and let's just justify all of those. All of this stuff is all about remapping those values and creating the domain. So I'm going to go ahead and just organize like so, or group all of this together. And this is all about making the box. So we'll right click and group those. Perfect. So now we've gone ahead and added our attractor objects and our attractor curve. We'll have a couple extra videos here that use the attractor, the boundary curve as an attractor, as well as going back to the very beginning and offsetting, because you'll notice some of the stellas push beyond our boundaries. We'll do that in a subsequent video. Move this boundary in a little bit so it removes any stellas that do hang over like so.